Welcome to the third lecture of formal models. Topic of today are Petri nets, a formalism that is used for describing distributed systems. In the last two lectures we have heard about finite automata, and we will meet this modeling language again, but this time we do not consider it on its own, but we use it for describing the behavioral semantics of Petri nets, as we will see soon. But before we formally introduce two variants of Petri nets, I would like to give you a short overview why Petri nets are of interest. So Petri nets are one of the most widely used modeling languages for describing distributed systems. Petri nets are pretty old, so they have been introduced in the 60s. And there is a huge community working on questions related to Petri nets, and therefore they are very well understood, and the theoretical properties are very clear. There are very basic variants, the classical variants that we will see today, but there are also many extensions that include, for example, colors, where tokens, a core concept of Petri nets, are distinguishable, but we do not have in the basic variant, where data types can be introduced and things like that. So these extensions are then tailored towards very specific applications. And so Petri nets are of interest because they can be used to describe a system in a rather straightforward way, and then they can also be verified. So the Petri nets is for sure an abstraction of the real system, but this abstraction can be checked for certain properties, and it can be verified that, for example, a deadlock can never happen, so that the system doesn't get stuck, or that some bad state is not reachable, or that it cannot happen that an event is never triggered. And for answering such questions, a lot of results are available, and also tools and algorithms that help to verify such properties. A very important application of Petri nets are their conciseness in the context of specifying other modeling languages, maybe not so formal languages, but languages that provide some freedom in their semantics. And one of the most widely used modeling languages that is based on the Petri nets semantics and the concepts found in Petri nets are UML activity diagrams. So we have seen, or we have shortly mentioned, that UML state machines are based on finite automata, so that many ideas found there are inspired by this formal modeling language, and in a similar sense UML activity diagrams are based on Petri nets. Okay, and before we talk about Petri nets and have a look how they are defined and how they work, we first have to do a short excursus where we introduce LTS, which is a special kind of automaton that will be used for defining the behavior of a Petri nets. And it's very easy to define a label transition system. It's just some kind of automaton that consists of the following component. We have a set of states S, we have a set of actions sigma, we have initial states, which are a subset of the states, and we have a transition relation, which is a subset of the cross product S times sigma times S. So from one state we go to another state where when some action is executed or when some event is happening. What we do not have, in contrast to finite automata, as you will certainly have realized, are the final states. These are missing. And this is because with LTS we are not interested in the question whether a word is accepted, a word over sigma star, a word over sigma is accepted. We are more interested in possible or allowed streams of action. So we have maybe a reactive system. Next slide, I have an automaton. And we are interested if the possible actions that can be executed by the systems happen in an allowed order or if there is some problem. Therefore, LTS are usually not complete because then everything would be possible. Instead, they capture only those sequences of actions that are allowed, and they are not necessarily deterministic. As we will see, they are even very often non-deterministic because this provides a very powerful way of modeling. Yeah, and we will use them to define the semantics of the Petri nets and to concisely characterize their behavior. And this is not the only application where we will see LTS in the context of this course. We will also see them later again. And but this is a very simple concept when knowing about finite automata. Yeah, so the main distinguishing feature with respect to finite automata is that in LTS we do not have any final state. Yeah, and here we have an example, which is a ticket machine. I will not go too much into details because it's basically a finite automaton where we have states. We have initial state P, we have state paid 5, we have print child ticket paid 10, print adult ticket, and these are the states, and then the actions are €5, €10, €5 again, press a button, and child ticket and adult ticket. Yeah. So what we have here is we have the modeling of a vending machine, and the vending machine accepts several kinds of input. So one input is that €5 can be put into it. Another input is that €10 can be put into it. Then we have the input that button can be pressed, and then we have the action taken by the vending machine that the child ticket or an adult ticket is printed. Yeah, and as we see here, this automaton is not complete. For example, when no money is in the automaton, then the button pressing the button does not lead to a state change, and nothing is happening. So there is no transition modeled. Yeah? Okay, and there is not much more to say about it because we know enough about it from finite automata, and this we will use for describing the behavior of a Petri net. We will not start with the introduction of the classical variant of the Petri net, but we will introduce first condition event nets, which are a very basic form and which is not the thing what one thinks about when hearing the notion of Petri nets, but it's a bit simpler, and for getting to know with the concept of Petri nets, it's very convenient, because it's a bit simpler. Okay, so Petri net, or in particular a condition event net, is also defined like an automaton in terms of a tuple. We have conditions C, which can be true or false. If they are true, then they contain a token. This also gives us the semantics and the behavior of a Petri net, as we will see. Then we have initial markings. These are those conditions which are true in the beginning. So the initial markings are, or the initial marking is a subset of all conditions and these conditions which are contained in the initial marking are true in the beginning. Then we have a set of events E, and in order to connect events and conditions, we have a dependence graph, which is built from edges from conditions to events, together with edges from events to conditions. Yeah, since these two sets are disjoint, we can use here the disjoint union to indicate that the two sets we have here have no common elements. Yeah? So what we have now is we have a kind of graph that contains two different kinds of nodes, the conditions and the events. And graphically, we represent the conditions by circles and the events by these boxes here. And if a condition is true, if it has a token, then we put a black dot into it. If it's false, then it's just an empty circle. And usually we also have some labels giving names to the conditions and the events, such that we can distinguish them and talk about them. Yeah, and here I have an excerpt of a dependence graph. We have here two conditions. They are connected to this event here, and this event here is then connected to this condition. In order to execute a Petri net, the interesting question to ask is when can an event happen? When we say when can it fire? And an event can fire if it is enabled. And in order to define what it means that an event is enabled, we have to give which preconditions have to be satisfied for an event such that it can be executed. And this is the one thing that is interesting. And the other thing that is interesting is what are the effects when an event takes place. So how does the state of the system change when an event has taken place or when an action is executed? Yeah, so I use the notions of event and action synonymously. Okay, and now I will formally define these notions of pre- and post-conditions for an event, which is rather straightforward. Assume we are given a condition event net, which is consisting of the components as we have introduced them before. And for each event, we define the preconditions, which we denote by G minus 1 of E. By this we denote the preconditions. And when we have done that, we define the postconditions of an event E, which we call G of E. Okay, and what are the preconditions? Yeah, the preconditions are simply those conditions which have an outgoing edge that leads to the event E. Yeah, so the preconditions are those conditions of a Petri net that have a pair CE in the dependence graph. Yeah, so from C there is an outgoing edge to E in the dependence graph. These are the preconditions. And for the postconditions, we have the following. These are all the conditions for which it holds that there is an edge from E to the condition. Yeah, so there is this pair EC in the dependence graph. E has an outgoing edge to the condition C. And what this basically means is that the preconditions give us those conditions which have to be true in order to enable an event. And the postconditions are those conditions which become true when an event has taken place, when it has fired. Before we look at a larger example later on, or also define the full semantics, let's have a look at some small examples. For this I need my writing space. To make the notions of pre- and post-conditions more concrete, let's look at this small artificial condition event net we have here. It consists of 3 conditions, C1 to C2 and C3, and 2 events, E1 and E2. The graph here shows how they are connected. And we want to identify the preconditions and the postconditions of E1 and E2. Let's start with E1. So we want to have the preconditions of E1, and for this we simply check what are the incoming edges and from where they come from, and the preconditions is simply the collections of those conditions. So here we have only one incoming edge which comes from C1, so we put C1 into the set of preconditions of E1, and only if the precondition is true, so if it contains a token, E1 is enabled and can potentially fire. For the postconditions, we have to look at the outgoing edges. E1 has 2 of them, and they lead to the conditions which are the postconditions of E1, and these are C2 and C3. Yeah? E1 can only fire if C2 and C3 have space to take the token, so if they're empty. And after E1 has fired, C2 and C3 contain a token, meaning that the conditions are true. So if there is one token in C1, then E1 is enabled because C2 and C3 are empty and it can fire. And if it fires, it takes the token away from C1 and puts token into C2 and C3. Yeah, then after the execution of E1, C2 and C3 become true. Now let's have a look at E2. There are the preconditions of E2. Here we have now 2 incoming edges, and therefore the preconditions of E2 are C2 and C3. And there is only one outgoing edge, so only postcondition is C1. Okay, and if there are tokens in C2 and C3 and space in C1, E2 can fire. What is the case here in this situation? And therefore, tokens from C1 and C3 are consumed, and one token is produced which goes into C1. And this principally shows us already the execution of this very simple CEN. And yeah, let's have a look. Let's have a detailed look at the formal semantics of this CEN and CEN in general. On this slide, I have the full semantics of a CEN, and for defining the semantics, we use an LTS, which describes as the state transitions of the system we are modeling with the CEN. Okay, so let's N be a CEN with condition C, initial marking I, events E, and dependence graph G. Then we define LTLs L that gives us the behavior of N as follows. We have the set S of states, which is the power set of C. So these are all possible sets that can be formed are all possible subsets of C. And we call such an element from the set of states also a marking. And intuitively, a state contains those conditions which are currently true. Yeah? And if the set contains all conditions, then are all true. If it contains no condition, then all are false. Then we have the initial marking, which is simply the set containing I. So here we have all the conditions which are true in the beginning. Obviously this is a subset of S. Then we have the alphabet sigma, which contains simply the events. And what's a bit more tricky is the transition relation, which we will now introduce, and which maps a state and an event to another state. Yeah, and since it's not deterministic, it's a transition relation and not a function. Okay, and what are the conditions that we can have such a step in the transition relation? Yeah, okay, so first of all, we have to ensure that the preconditions are true. Yeah, so we have, when we want to execute an event, when an event should fire, then first of all, it has to be the case that all the preconditions are true in the current state. Yeah? So if G minus 1E is the set of preconditions, then this has to be a subset of the conditions that are true in the current state. Only if this is the case, an event can fire. This is the first condition. Then in the second condition, we have to ensure, and this is a typo, this should be a cup, yeah, so this should be the intersection. Yeah. So if we have the post conditions, then all of them are empty, so they are ready to take a token. Yeah, so the intersection of the post conditions and the current state is empty. Yeah, so all of them can take a token. And then finally, we have to define how we update the conditions when event E fires. And this is also not so complicated, even though it's a bit complicated written down. So what we take is, we take the markings that are, we take the marking we take the marking C1 and remove all conditions that are in the set of preconditions. So the preconditions become false after event E has fired, and the post conditions, they all become true. So the token is removed from the preconditions, and the token is then added to the post conditions. This is the state update, and let's have now a look at some example. I need again my writing. Yeah, assume we have conditions A, B, and C, and they are preconditions to event E. This is event E, and then we have one post condition D. Okay. Yeah. What happens if we assume that here in C is a token, here in B is a token, and here in A is a token? Come from somewhere, and then we proceed somehow. Then in the LTS, we simply would represent the state as A, B, C, because these are the conditions which are true. Since D does not have a token at this time point, it is not true in the current state and therefore not considered. Now when A fires, we add this as a labeled edge in a labeled transition system. Now we have to update the state. A, B, and C become empty. the preconditions become false, and D becomes true. So in the next state, D is the only condition that is true. And then we somehow proceed. Let's consider another example. Assume we have the following. We have we have two events, E and F, and one condition, A again, and yes, it proceeds somehow, and F goes to B and to C, and E goes to D, and somehow proceeds. So, and assume we have one token in A. So the current state is simply A, and then all preconditions of F are true, and all preconditions of E are true. And at one time point, it's not possible that two events fire, but only one of them. So now two things can happen. In this state, we can either do an F or we can do an E. In case that F fires, A becomes false, and B and C become true. D is untouched, so there nothing changes. And in case E fires, A also becomes false, but then D becomes true. Yeah? So this is how the excerpt of the LTS looks like in this second scenario. Now assume we have the following situation. We have a token A that goes to an event E, and A goes also to F, and there is a condition, so A is a condition, and also B is a condition that goes to F, and only in A is a token, and then we put a token here into C, and assume C is also some input to F, and E produces also a B. Okay? So in the current state, only A is enabled. When A is enabled, then E can fire. If E fires, A becomes false and B and C become true. What is about F? If only A is true, then it cannot fire because preconditions B and C are not true. Now we can check what is happening in PC. Now conditions B and C are true in this state. But maybe let's update it in the picture. So when E fires, A becomes false and C and B become true. So this is the state BC. And then it's clear that E cannot fire because there is no token in A. But also F cannot fire because there is no token in A. There are now tokens in B and C, but no token in A. Therefore, we are at a dead end and cannot proceed. Then there is another example I would like to show you, which often causes problems. So assume we have conditions A and B, and both have tokens, so both are true. They go to an event E, and E produces an output token in C and D somehow. now but assume that there is already a token in C. Yeah? So we are in state AB, and then it's not possible that E fires because the post condition here is already true. The post condition C is already true, and therefore this condition doesn't have the space to take a token. Yeah, and therefore A cannot fire. And for this reason, we also get stuck here. Yeah, these were the small tiny examples which I wanted to show you to get a first impression how the execution of a Petri net works and how this is realized in terms or represented in terms of an LTS. And in the following, we will have a look at a larger example which is also a bit more related to practice. The example I show here is a producer-consumer example where we have the producer here on the left and the consumer on the right. And the producer produces some output which is then processed by the consumer. The consumer could be, for example, a printer which receives print jobs, and the producer could be some application that provides documents to be printed. And those two subsystems somehow communicate with each other and exchange information, and obviously the direction is that the producer sends something to the receiver and the receiver processes it. Here we do not have a big buffer which stores elements if the consumer is idle, but we have only one element that can be processed and scheduled at the time. Okay, but this could be extended. Let's have a quick look. What are the elements of this CEN? We have events: produce, deliver, receive, and consume. This is not so surprising. And what we also have are the conditions. Here we have a condition which I called A, which is true if the producer is ready to produce something. Then we have condition F, producer finished. If the producer finished, it is ready to deliver a document, but for this busy has to be false, so here has to be a space in B. If the consumer is idle and there is something in B could also be buffer, then receive can fire. It goes here, the token goes here to H, and then consume can fire. Okay, let's start with an LTS, and yeah, as I said, you will finish this in the exercises. Okay, so the initial marking is F and I, so the producer just has produced something and the consumer is idle, and so is ready to do something. Okay, what can fire in this state Fi? Yeah, here we have F as a precondition of deliver, D, and both conditions are empty. Therefore, D can fire. And now let's check if something else can fire. Here on the left hand side, no. On the right hand side, also no, because receive would also need a token in B, and this is not the case. Okay, so if D fires, then the state is updated as follows. F becomes false, but A becomes true and B becomes true, and the other conditions remain unchanged. So we have ABI. Now let's check what we can do in state ABI. And now we can do a bit more. We can do again a P and produce something, and now here receive has both preconditions satisfied. There is a P and an I, and therefore and also H is empty, therefore we can also execute, and R can also fire. Okay, so let's first consider the case where P fires. If P fires, A is consumed and we get a token into F. So this one is consumed and we get a token here, and the state updates to BFI. Okay. Then if we are in state BFI, what can we do here? Yeah, in this state, it's not possible to do a D because B is full. The only thing we can do at this point is we can do an R because B and I are true and H is empty. So we can do here an R, and if we do an R, the B is consumed and the I is consumed, and the token is put into H, so we get FH. And if we are in FH, what can we do? Yeah, we can do a deliver because the input, the precondition of D is satisfied and A and B are empty. So we can do a D here, or we can do an H here because H is true, it's the precondition of C, and I is empty. Okay, what do we do now? Yeah, let's say we do the D, then the F becomes empty and A and B become true. So we have A, B, H. And here I made a typo, we have a C here. Okay, ABH. And what can we do in ABH? Aha, we can do again a P, because we have our precondition satisfied of P, and we can then put the token into F, or we can do, what can we do as well? Yeah, we can do the C, and we get this token away, and we get, let's do this, we do this token away, put a token there, we do a C, and we get P, A, B, I. We have this already? Yeah, this we already have. This is here. This is what we get when we do a C. Yeah, and then we have to proceed here and here and here. And with this we can, when we do it until the end, what is your task, we can model all reachable state of this system. Yeah? And what is interesting in such a case is if there can be a deadlock, so that there is no way to event. In a minute we will define what is a deadlock. In this system there shouldn't be a deadlock. But it's your task to find out if this is really the case. As I already mentioned, it can happen that there is a deadlock, so that's for some reason the system gets stuck. And here on this slide I formally define what a deadlock is. First of all, I give a concise definition what it means that event is enabled in a marking so that it can fire. And we say that an event is enabled in a state S, in a state M or marking M, if and only if if and only if there is a successor state that can be reached when E is executed. Yeah, so there are transitions starting from M executing E that lead to successor state M prime. So this set of successor states when executing event A is not empty. Then an event is enabled. And we call a marking M a deadlock if it's a dead end in the LTS, so if we cannot further proceed. If there is no event enabled in marking M, what is the same if all events are disabled, or if we use the definition of above, that for all events E, it holds that they do not have any reachable successor states. And a CEN has a deadlock if there is a marking that is reachable, if there is a marking that is a deadlock and is reachable. Yeah, let's look at some small example, but this is rather straightforward. Let me switch to my writing. Consider the following scenario. We have conditions A and B, which go into event E, and A goes also into event F, and F produces a token that ends up in B, and E produces a token C, which is also some input to F, something like that. And assume we have the initial marking A, B. So in the LTS we start with A, B. Then what can fire? F cannot fire because C is not true, but A and B enable E. There's also space. So we do E, and this means the token go away from here and here, and we get the token in C. Okay, and now we have a C here and no other token. Okay, so the precondition C is satisfied for F, but now we have the problem that the precondition A does not hold anymore. Okay, and therefore we cannot proceed. So we are stuck here. And there are different scenarios where it can happen that a system gets stuck, but overall this is a behavior that is not desired, because the system should always work and should not end up in a state that is a dead end, and properties like this can be verified automatically. But we will not go into details how to verify Petri nets, but we will now introduce place transition nets, which are the classical form of Petri nets. The conditions in the CEN can either contain a token or they can be empty, meaning that the condition is true or false. We now will see a generalization, the place transition nets, PTN, which are the classical Petri nets, where this restriction on the capacity of a condition is relieved, and we can have multiple tokens in one of such conditions, but now in the context of place transitions nets, the conditions are called places, and these are specified together with some capacity indicating how many tokens they can take. So a place transition net is very similar otherwise to the CEN, but with the difference that we have capacities not only on the places which are similar to conditions, but also on the connections. And let's go over the final definition. So for a place transition net, which is the classical Petri nets, we have places, P, we have an initial marking, we have the transitions, which are not to be confused with the transition relation. The transitions here are similar as the events in the CEN. Then we have the dependence graph or the connection graph, and we have the capacities. And let's see how this is defined. So we define capacities for the places and for the elements of the connection graph G, and these are mapped to the natural numbers together with the infinity symbol. If we do not give any value for the places, then we assume they have infinite capacity. If we do not give any value for the connections, then we assume their capacity is 1. Note that the value can be specified for connections which go from a place to a transition, as well as for connections which go from a transition to a place. Yeah? And that's basically the difference. In the graphical representation, there is almost no difference. For the places, we can have now multiple dots, multiple tokens in the big circle, and we have additional information which we need to provide. So we need to annotate the places with the capacity, and we need to annotate the connections also with the capacity. And intuitively, the capacity of a connection means if it is an incoming edge for a transition, then it means that a certain amount of tokens is required for making the transition active. And if it's on an outgoing edge, then it means that a certain amount of tokens is produced. Yeah? Let's quickly go to my writing, then I will show you in detail how this looks like. So for example, if we have a place, then if we put the 3 here, then this has capacity 3. If we have here another place and put nothing here, this means that the capacity is infinite. If we have an edge to a transition T, and say here is a 2, then this means this connection has capacity 2, and if we put nothing here, then this connection has capacity 1. And the same here. If we put, for example, 5 here, and here we have a place with capacity 7. Yeah, and now assume we have 1 token here and 1 token here. Then in this situation, the transition T cannot fire because it needs 2 tokens from, let's say this is A, this is B. It needs 2 tokens from A, therefore it cannot fire. If we have 2 tokens in A, this is now a different situation, then it can fire. So assume we have a marking A is 2 and B is 1. Then T can fire. And say C is 0. T can fire. And the new marking is A is 0, B is 0, and C is 5. Yeah, this is the execution semantics of a PTN. And if we write this in terms of an LTS, note this is really just an excerpt and an example. We will do this more formally soon. If we have the state as before, we have A2, B1 and C0, this we do not write down. Then T can fire. it consumes the 2 tokens from the A, it consumes the token from the B, and produces 5 tokens from C, for C. And yeah, this is what we obtain. Now let's have a look at the formal semantics. This slide might look a bit complicated on the first sight, but in fact it's not much different than the semantic definition we had for the CEN. We only have to take into account the capacities, but what we do here is also we define preconditions, postconditions, and state updates. How does this work in detail? So we are again given a PTN with places P, initial marking I, T is the set of transitions, G the connection graph, and C the capacities, and this gives us an LTS that describes the behavior. We have states S, which is a collection, or which is a set of markings, and now a marking is a function that maps each place to a natural number. And the set of all such functions we denote by n to the power of p, meaning that we have here all functions from p to n. And this we have already seen in the example. We use this in the LTS, where we use this notation, name of the place and the number of the tokens that it currently contains. Yeah, these are the markings. Then the alphabet are simply the transitions, and here the TL, the transition relation of the LTS, which is not to be confused with the T of the PTN. Here we can do a transition from a marking M1 with a firing event E to a marking M2, if and only if. Yeah, first of all, we have to check if there are enough markings in the preconditions. Yeah, so we have again this G-1, which gives us the precondition places of a transition. Yeah, so for all places that are preconditions of T, it has to hold that they have enough markings with respect to the capacity of the outgoing edge of the place. Yeah? So if we have a connection from P to T, then this connection has a capacity, and this capacity has to be smaller than the current number of tokens in P. Yeah, so the first condition says we have enough tokens in the preconditions of, this should be a T. So this is not event, this is a transition. And the second condition says that we have enough space in the post conditions. So for all post conditions, it's the case that if we have the number of the current number of tokens plus the number of the produced tokens, so this is the capacity of the edge that goes from T to Q. If this has to be smaller than the capacity of Q. Yeah, so there has to be enough space in the place Q. So this means there is enough space in the post conditions of T, and then we do a state update, and what we simply do is we have the markings. We have the markings that are of places that are in the preconditions. We have the markings that are in the post conditions, and we have unrelated markings. And for the markings in the preconditions, we have to remove the numbers of tokens that is used. For the markings in the post conditions, we have to add the numbers of tokens that is produced, and otherwise nothing is changed. And this is what the formula here says. Let's have a look at an example.
Let's call the given Petri net N, and N has two transitions, A and B. A has capacity 2, this means it can take at most 2 tokens, and B has capacity 4, which means that it can take at most 4 tokens. Then we have transitions E, F and G, and also the edges, or some of the edges, are labeled with weights. For example, the edge that connects E and B is labeled with a 2, saying that E produces 2 tokens when it fires that go into B, or here this edge from B to G is labeled with a 4, saying that there have to be 4 tokens in B in order to make G fire. Yeah, and if there is no label on an edge, this means that the weight is 1, and if there is a place that is not labeled with a capacity, then this means the capacity is infinite, so an infinite amount of tokens can be put into the place. Yeah, now what we need is some initial marking. Let's put 2 tokens into A. If we put tokens somewhere else, then the execution would look different, but we start with 2 tokens in A, and this also gives us the initial state of the LTS. Therefore, there the initial state is now A2, and now let's see what can fire if we have 2 tokens in A. F cannot fire because B is empty, same for G, but E can fire. It needs 1 token and 2 tokens go into B. So if E fires, let's mark it in red, 1 token goes away from A and 2 tokens go into B. Let's use red. Okay, so here in the LTS we add an edge labeled with an E, saying if E fires in state A2, we go into state A1, B2. Okay, then we're done here. If we're in state A1, B2, then we have to look what can fire. Now F can fire and E can fire because now there is 1 token in, there are 2 tokens in B, so F needs 1 token, and there is also space for 1 token in A, and E can also fire because there's 1 token in A and still space for 2 tokens. To indicate this, we say that F can fire and E can fire. Let's proceed with F. So if F fires, 1 token goes away and 1 token goes away from B, and 1 token is added to A. So the colors here of the tokens do not have a meaning. And then we have the state A2, B1. I keep the edge here on the right open for a moment. I come back to this one later. Okay, so we are now in state A2, B1. What can happen here? F cannot fire because there is no space left in A. G cannot fire because there are no 4 tokens in B, but E can fire. It takes 1 token from A and puts 2 tokens into B, so we go into state A1, B3 by fire when E fires. Okay, if we are in state A1, B3, what can fire here? Yeah, here F can fire. What else? E cannot fire because there is not enough space in B. 3 plus 2 would give 5, which is larger than 4. And also G cannot fire because there are no 4 tokens in B. So only F can fire. And if F fires, 1 token is consumed from B and 1 token goes into A. So we have A2, B2. And if we are in this state, and now I do not overlook it, F cannot fire because A is full. G cannot fire because no 4 tokens are in B, but E can fire because it can take 1 token from A and put 2 tokens in B, and 2 plus 2 is 4, so there is perfectly enough space in B. So if E fires, then 2 tokens go into B, and we are in state A1, B4. With E having fired. Okay, in this state, now G would have enough tokens in B, but it cannot fire because there is not enough space in A. So G cannot fire. I missed 4 here. What about E? E would consume the 1 token from A, but E would consume the 1 token from A, but there is not enough space in B. F can fire. F can take 1 token from B and put another token into A. So then we have F and get into state A2, B3. In this state, F cannot fire because there is no space left in A. Also, E cannot fire because the capacity of B is too small. It cannot take 5 tokens. And also G cannot fire because there are only 3 tokens in B, but 4 would be required. Yeah? So therefore, we cannot proceed from A to B3. And now we have to close the path from A1, B2 when we get an E. So let's modify the marking such that we can see it easier. Okay, if we have 1 token in A and E fires, then this 1 token goes away and 2 tokens, so E fires, and 2 tokens go into B, so we get a B4. And if we are in state B4, then finally G can fire, and it takes all 4 tokens of B and puts them into A, and puts 2 tokens into A. So if G fires in this state, we go to A2. Question is there something else that can be done when we have 4 tokens in B? Obviously, E cannot fire because no space is left in B, but F can fire. It can take 1 token from B and put 1 token into A, and then we have A1, B3. And this is what we already have here. Yeah, okay, and with this we have the LTS of the Petri Net, and with this I would like to conclude this lecture. Thank you very much for watching.